as I said, I changed the title a bit, so the end of the POSIX file system, or maybe not, so we'll see. And I had a subtitle, reflective a bit on what is happening between companies in the industry. So the CEO of NVIDIA said, we buy this networking company because it's all about the future data center, and the future data centers will look like HPC data centers. So it's storage and the HPC data center, or it's actually HPC storage and the data center. We hope for the latter, of course, given that HPC is a slightly limited market. I'll start with two caveats. So this is a vendor presentation. So it's supposed to be boring, so don't complain. And this is not a visionary presentation. So somebody said to me recently, if you have visions, go to the hospital. So I'm not doing visions here. We don't really talk about HPC data centers, but there is cloud data centers, and they look very different from what we do. We do still everything in bare metal. The cloud data centers do everything virtualized, the network, and your IP address on your server, I'll change that tomorrow, depending on how provision it, so don't use that for your failover. And on the HPC side, we still store most of our data in shared POSIX file systems that are these large monolithic things that somebody sets up and then nobody hopefully ever touches again, or only if something goes badly wrong. We use a bit of SSDs in HPC, but it's still mostly metadata. I know it's coming, I will talk about that. We all have played a bit with things like Hadoop and object stores and all that stuff, and it all didn't work, so we don't really use it in production. Maybe sometimes, we pretend we do, but we don't really do. And yes, sort of the large sites have special ways to deal with storage, so they use special performance and capacity tiers and special software that is, expensive and difficult to implement, but, the general little HPC center at the university doesn't have those budgets, so everything is much simpler. As I said, on the cloud side, everything looks very, very different. Most of the data probably lives somewhere in a local file system on a virtual machine, now increasingly SSDs. People do use object stores, but they usually use it for very large monolithic applications, not for running lots of applications. So if you start building one application and that's all you do in your lifetime, then object stores may not be so bad. But there is also sort of the entire opposite. So there is still enterprise storage that has special things like, microsecond failover, and so that is still being used even in hosted cloudy environments. And tiers and cloud data center are mostly, things that are used for redundancy, backup, retention, or so. We don't really do those things actively. I was asked to talk a little bit about Exascale. So yes, those projects are finally coming. Lots of them. There's probably 20, 30 or so that we engage with on a daily basis. Maybe more actually. But the requirements for those look pretty much like the requirements looked like 10 years ago or 15 years ago or maybe 20 years ago. From a storage perspective, I can't talk about compute. We are sort of the little step-child in the market. But that said, when people talk to us about Exascale projects, it's still, for the most part, very classical HPC compute-centric driven. And I wonder a bit, and I'll talk a little bit about it, what the actual requirements, when those systems are being run, will actually look like. And, I think that some of them may look quite different. So yes, there are new applications. Somebody was talking about AI earlier. And those applications actually have implications, quite significant implications for storage and data management. But let me talk a little bit about the classical stuff. So this is, you all have seen this. So I'm borrowing a couple of slides from John Bent, as some of you will probably see. So this is from Los Alamos 2016. So how will HPC storage look like? I'm not going into too much details here, except we at DDN did something similar a couple of years ago. We had this wonderful slide that said, you have this fast tier and then this semi-fast tier and this slow tier and this very slow tier. The background here is, of course, 20 years ago with the ASCII project, when parallel file systems sort of were conceptualized, you had this nice thing that gave you a unified storage space for all of your applications, so you didn't need to do complicated stuff like tiering and all of those things that we didn't like to do 20 years ago. And then, you just connected it to a tape archive, and that was it. Now, this is another sort of famous set of graphics. SSDs used to be complicated, so the whole parallel file system couldn't be SSDs, so we had this thing called a burst buffer, whatever that really means. And then some people conceptualized and said, well, if I look at tapes and the performance requirements I have for tape compared to the cost, then actually I might be better off with yet an additional tier that was then called campaign storage. So we ended up with those layers and layers of storage that all had good reasons to be there, until somebody said, well, we actually don't want tiers, and tiers are just an unfortunate accident of the economics. All we want is a lot of memory, and a way to get my data out of memory somewhere else at best. So this we call now Lang's law after Michael Lang from Los Alamos. So fewer tiers, fewer tiers. It isn't that bad, but now we are back sort of to, we have a fast thing and then we have an object store behind. This is from NERSC. It's a bit similar. So, today we have all of these tiers, and, we'll slash them together again, and we end up with something that's integrated with my compute system and something that's just separate from my compute system. So platform integrated storage, off-platform storage. All this is fine and great. Now, just two things. This is data from sort of internal pricing for SSDs and drives. It's just relatively printed. This is our supplier pricing, actually. And you can see that the SSDs are becoming cheaper and cheaper and cheaper. And yes, there is now quad-level flash that is super low endurance. That's 0.1 dBPD or lower. But it's still expensive, and it's still, even quad-level flash is 4 to 5 times of a drive. So most likely, some other tier will remain for some time. This is a couple of systems that we did recently. These are all fairly large systems. What this shows is the sort of the real-world flash to spinning media capacity compared to flash to spinning media bandwidth. So yes, I can get a lot more bandwidth out of flash. It's a lot cheaper now. Devices are becoming faster, but the capacity is still expensive, and real-world deployed systems are somewhere between 5, 10, maybe 15% of flash capacity. So, maybe some tiering may not be so bad. And, yes, we have used buffer caches and things like that for a long time. So, maybe there is an argument for tiering. Like usual, tiering works quite well for certain types of applications or certain types of application workflows. All the way from well, checkpoint restart to, it could be a local device with a library or, some sort of burst buffering, all the way down to new types of applications that are very, very read-centric. And I'll talk a little bit more about that. So, if I relax my notion of tiering and I go from a very strict notion where everything needs to go through this one tier, so this fast tier, to a notion that's a bit more application workflow specific, where I say certain workflows I'll benefit from a fast tier or a flash layer. Other workflows I don't benefit, so I don't use them. And I think this is kind of where people are today as they're experimenting in HPC data centers with larger and larger flash systems. So we have delivered probably 40, 50 flash systems that are significant, meaning on the order of a petabyte or more. There are systems of 5 to 10 petabytes coming in the next 1, 2, 3 years, here in Europe, in the US, everywhere. And I think one area that everybody is a bit interested in is what's the benefit of those systems and when do I benefit from those systems? So when does the additional cost actually give me real benefits? Now going back to this slide from Los Alamos, there is the other side, which is the object store. So again, this is a nice slide from John Band. So if I'm alone on an island and there is no connection to anything and somebody says, build me a storage system that can store 1 trillion of things, then sure, I'll probably build an object store. But the reality in the world is that the typical requirements for object stores, if I go into the details, it's like, yes, immutable, transactional, get, put, trillions of things, fine, but then it gets complicated. I want named objects. I want to group objects into logical things. I don't need directories, but I still want to group them. I want to nest them within each other. I want to have the same object appear within multiple collections of things. I'm in HPC, so I have this large file, so I want to do multi-threaded write, so I don't want to write my 1 terabyte file as one thread. And I want to tag and do all sorts of stuff with those objects. So, well, in reality, this isn't all that different from files. It's a bit simpler it's actually a bit simpler to build, which is why a decade ago we had literally hundreds and hundreds of projects to do object stores. Everybody was doing their own object store because it's so much easier to do. But in reality, very few of those actually have survived. Since we don't live on an island and we are not isolated from applications and things that people use today, what's the real lesson from object stores? And the real lesson from object stores is, well, there are situations where POSIX can be relaxed just a bit to make my life as a storage programmer or developer just a bit easier and to give you as a user something that is more performant than what you had before. If I had those things like rename in a POSIX file system is a very hard thing to do. So if I relax certain things just a bit, suddenly, I can give you capabilities that you didn't have before. So the real lesson of object stores, probably is something different. So this is what I call Band's law for HPC storage. So the future is bright, and most less we predict it, well, hopefully. But don't be scared by POSIX. And embrace certain relaxations. So people have talked about that for a long time, but finally we have proposals to say, here is 2 things I don't do, and are you fine with that? And then are you not fine with that? Maybe you'll just change that application that isn't fine with that. And also don't be scared by tiering, but embrace certain relaxations and don't necessarily force your users to tier all the time. Now, that's all good for HPC storage, but there is more. So a couple of years ago, we did an internal survey of parallel, shared POSIX file system users. And one of the results was that, give or take, 50% of those users aren't just classical, tightly coupled HPC simulation type of users, but are users that have lots of data and run lots of little tiny jobs, sometimes a million of them, so tens of millions per day, to do, read a piece of data, do something, write it back. Or they do what many smaller HPC sites or universities do, not necessarily the DOE sites. They have just all sorts of stuff happening, from a weather code to a life science end user, and they run the same system. So if you look at this, so this is really where the main market for shared scale-out storage is. It isn't the classical HPC market, it's a broader market that is increasingly data-centric. So this is a bit similar. So this is some data from the 2018 Lustre end user survey that's done every year by OpenSFS. So you see machine learning, life sciences. Sure, there is classical HPC like weather and climate, but there is other stuff there that is being used by end users on shared POSIX file systems. So if you look at the HPC data center today at the volume, meaning if I look at our user basis, for example, of what happened in the last decade, then certainly what I call research big data is something that has dramatically changed how people use storage. And it's a fairly large market, for us actually by far the largest market, and it's very different from classical HPC, because as I said, it isn't like a tightly coupled simulation that writes to one file, but it's lots of stuff that is happening by lots of applications, lots of users with different types of data. And many of those data centers dedicated to analytics and deep learning, for example, they look actually much more like large cloud environments. Some of those, large Silicon Valley companies that have large deep learning environments, they're essentially a cloud environment, but they still use a large or, a couple of 10 or 20 or 100 large shared POSIX file systems in the back. And these are some of the largest users of those environments today. The whole environment from a management perspective, from an end user perspective, is already dramatically changing in a way that goes a bit away from the classical HPC data center. Of course, we will still retain the classical HPC data center, but those changes are coming. And yes, so end users are increasingly running certain types of applications in cloud environments. Usually those are not data-intensive applications. So, for example, the end users we have running cloud environments typically are enterprise analytics users who have relatively small data sets, usually of tens of terabytes or a couple of terabytes, but who still use a shared POSIX file system because that's what the application wants. And if they have hundreds of terabytes of data or petabytes of data, they will move off the cloud simply because the cost of managing data in the cloud is actually quite expensive. So there are new requirements that are coming. So environments are changing in the machine learning, the deep learning storage market, and also the I/O requirements are shifting. So suddenly we do lots of random reads, small random writes maybe, but certainly not shared bulk data writes like in HPC. So yes, I do benefit from SSDs at peak time. Yet at the same time, all of these end users, if they do significant work, typically have very large data sets, up to hundreds of petabytes of data sets. So the environments that we see are going from, I have one little system here and I use local NVMe, 2, I have lots of systems, and I use essentially a shared POSIX file system. 2, a new way where I combine things. So I have a global capacity shared file system, but I also use my local node SST in an interesting way, in a dynamically provisioned way, or I use remote NVMe devices with NVMe fabrics, and again do interesting things with my storage environment. So the first time I have heard about sort of dynamically provisioned file systems was in 2014 in a talk from Lawrence Livermore, where the idea was, could I do a file system per job with staging data in and out? And there are certain benefits of that. I isolate this job from other jobs. I increase my metadata performance for sure, since now I have one thing that I need to care about, not 100 things. And there are very other things that people have done. So it isn't very well known, but Fujitsu with the K computer did something quite exciting. So they had this enormous Lustre file system with like 1,000 servers that didn't work very well because only had one metadata server. So they changed the entire storage usage to a model where all of the data was staged into loopback devices on a per node basis, and that way increased our metadata performance significantly, but made it very complicated to use because now you had to stage in your data into your loopback devices. Other people have used similar things. Amazon has announced a Lustre service that's available, well integrated. We, before Intel, VMcloud, have had users on Amazon, Azure, Google, using dynamically provisioned file systems for a long time. And there is a lot of future technology that is coming. In the Lustre world, for example, there is an interesting project that will package data into container images that are then auto-mounted and integrated in the file system metadata environment. So it's a bit like a loopback device, but it's a loopback device that's transparent to the namespace. And again, in the Lustre world, there is a new feature called Lustre on Demand that we have deployed for the first time just a couple of weeks ago with a genetics user in Japan. So where does this leave us for the future? Well, sure, you can go to Amazon, but you will find that the user limitations do apply. So the usual limitations for cloud is my server is now not 10 gigabytes per second, but 500 megabytes per second, and I need lots of them, and it's actually very, very expensive. So what we think where the future will be is, so yes, there will still be POSIX file systems, lots of them, but they will look just a bit different. They will increasingly have portions that are much more dynamic than they are today. There will be file servers that essentially are just container images that run on one server in one moment, or on 100 servers, on 100 nodes in the next moment, in an automated, provisioned way that your environment manages. It will still be POSIX, but we'll relax it a bit where we need to relax it. And there will still be tiers, but again, we'll reflex those tiers and we relax standards according to what the application workflows requires. So the environment will look a little bit like this. It's one storage environment managed as one thing, but it will have many different things that happen depending on your application workflows, your applications, your users and your user requirements. So we'll add to the relaxed tiering and the relaxed POSIX a dynamically managed system integrated storage environment. Is that back to the future? To some extent, yes. It remains, I think, what we do best today, but with some twists that I think will help us to manage new types of requirements better than we do today. So with that, I'll thank John Land for most of the content, and Tommaso for the title and the abstract, and the rest is all my mistakes. Thank you.